Let's set the stage. It's 1915. The world is in the midst of great change, with new ideas and discoveries reshaping how we see everything around us. In a small office, Albert Einstein unveils his general theory of relativity, redefining gravity not as a force but as the very curvature of space-time itself, a radical shift in our understanding of the universe. Hidden in his elegant equations was a wild, almost unbelievable prediction. The universe isn't silent, but alive with invisible vibrations. Cataclysmic cosmic events like exploding stars and colliding galaxies would send ripples called gravitational waves through the very fabric of space-time. Imagine two black holes spiraling together in a cosmic dance, churning space-time and sending out waves that travel across the universe at the speed of light, carrying the story of their collision. For a century, this idea remained just a theory, an elegant ghost in the machine, haunting the dreams of physicists and astronomers. The challenge was immense. By the time these waves reached Earth, their effect would be smaller than a proton's width, so tiny it seemed impossible to ever detect. Detecting them seemed like trying to hear a pin drop in the middle of a hurricane with the universe itself roaring all around, yet generations of scientists refused to give up. Driven by curiosity and the hope of proving Einstein right, they built ever more sensitive instruments, pushing the boundaries of technology and imagination. Then, on September 14, 2015, after decades of effort, LIGO's detectors felt a tiny, fleeting chirp, a tremor from two black holes colliding over 1 billion light-years away, echoing across the cosmos. For the first time in history, we didn't just see the universe, we heard it, tuning into a cosmic symphony that had played for eons. We had detected a gravitational wave, a ripple in space-time itself, confirming Einstein's boldest prediction. Einstein's whisper after traveling 1.3 billion years across the universe had finally reached us, changing our understanding of reality. The game had changed forever. Science had crossed a threshold, opening a new era of discovery. The universe had spoken, and for the first time we were finally listening, ears wide open to the music of the cosmos. This was more than a scientific milestone. It was a new way to experience reality, a new sense added to our perception of the universe. The impossible had become real. What once seemed like science fiction was now science fact. The cosmos had revealed a new secret, inviting us to explore mysteries we never even knew existed. And our journey had just begun, with endless wonders still waiting to be discovered. So, what exactly are gravitational waves, and why are they so important to our understanding of the universe? Imagine space and time not as separate things, but as threads woven together into a single four-dimensional fabric, what scientists call space-time. Massive objects like the sun or even entire galaxies bend and curve this fabric, creating what we feel as gravity. Now picture two incredibly massive objects, such as black holes or neutron stars, locked in a cosmic dance, spiraling ever closer together. As they orbit, they disturb the very fabric of space-time, sending out ripples that travel across the universe. These are gravitational waves. These aren't waves moving through space like sound or light, they are waves of space itself, stretching and squeezing the universe as they pass. To help visualize, think of the universe as a perfectly calm pond, its surface undisturbed and smooth. Now, throw in a massive stone, like two black holes colliding, and ripples spread out from the impact, traveling across the pond. The bigger and more violent the event, the larger and more powerful the ripple that spreads out. Gravitational waves stretch and squeeze space-time itself as they pass, distorting everything in their path, even distances between atoms. If a gravitational wave passed through you right now, you'd be stretched in one direction and squeezed in another. Then the effect would reverse, all in a fraction of a second. But don't worry, the effect is so incredibly tiny, far smaller than the width of a proton, that you'd never notice it happening. This rhythmic stretching and squeezing is the unique signature that scientists search for in their data, a cosmic fingerprint left behind by these waves. It's the telltale sign that a ripple in reality itself has passed through us, a fleeting distortion in the fabric of existence. Only the most violent and energetic cosmic events, like black hole mergers, neutron star collisions, or titanic supernova explosions, create waves strong enough for us to detect here on Earth. Black hole mergers, neutron star collisions, supernovae. These waves don't just carry energy, they also carry information, revealing secrets about their source and the nature of gravity itself. By catching these waves, scientists can learn about the most extreme and mysterious events in the universe, events we could never witness with light alone. Gravitational waves are the universe's way of sending us messages from its most secretive and hidden corners, places light can't always reach. They're not just a new kind of signal, they're a revolutionary new way to understand reality, opening a window into the invisible universe. And now, for the first time in human history, we have the technology to listen to these cosmic whispers. The universe's deepest mysteries are finally within reach, waiting for us to discover them through the echoes of gravitational waves. Detecting a signal that stretches space by less than an atom's width is a monumental challenge. Imagine trying to sense a ripple so subtle, it passes through everything, matter, light, even you, without leaving a trace. Yet this is exactly what scientists set out to do. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. It's not just a building, but a marvel of human ingenuity, designed to catch the faintest tremors in the very fabric of space-time. LIGO isn't a telescope, it's a cosmic microphone listening for space-time's faintest hums. Instead of looking up at the stars, it listens for the echoes of cataclysmic events, like black holes colliding billions of light-years away. Each LIGO facility is shaped like a giant L, with two 4-kilometer arms in a vacuum. These arms are so long they stretch across the landscape, almost vanishing into the horizon. A laser beam is split and sent down each arm, bouncing off mirrors and recombining at the corner. The setup is so precise, even the tiniest vibration or temperature change must be accounted for. If a gravitational wave passes, it stretches one arm and squeezes the other, changing the distance the lasers travel. This difference is unimaginably small, less than 1,000th the width of a proton. This throws the system out of balance, creating a flicker of light, the signal. That tiny flicker is the universe whispering its secrets. Two detectors, thousands of kilometers apart, confirm the event isn't local noise. Only when both hear the same signal do scientists know it's real, a cosmic event, not just a passing truck or a gust of wind. The 2015 detection was the result of decades of effort, pushing technology to its limits. Teams of scientists, engineers, and visionaries worked tirelessly, overcoming setbacks and skepticism. LIGO turned Einstein's prediction into a measurable reality. What was once just a theory became a discovery that changed our understanding of the cosmos. We built an instrument sensitive enough to hear the universe's whispers. It's a testament to human curiosity and our drive to explore the unknown. And with it, we opened a new era of discovery. Now, we can listen to the universe in a way never before possible. The universe's secrets were finally within earshot, and a new chapter in our cosmic story had begun. The first gravitational wave detection, GW150914, was more than a technological feat. It was a triumph for Einstein's theory. For a century, general relativity had passed every test in our solar system, but never in the chaos near black holes. LIGO's signal matched Einstein's predictions perfectly, even in these extreme conditions. It was the ultimate stress test, and general relativity passed. This wasn't just about confirming a theory. It proved our understanding of gravity holds up in the wildest corners of the cosmos. Einstein's map of the universe was right, even where we'd never looked before. Before gravitational waves, black holes were phantoms, seen only by their effects on nearby matter. Gravitational waves changed that. Now we can hear black holes merge, revealing their masses and spins. The first detection showed two black holes, 29 and 36 times the Sun's mass, merging into one of 62 solar masses. The missing mass, converted to pure energy as gravitational waves, ELMC2 in action. The waveform's details let us measure not just mass but spin, how black holes twist spacetime. This data is crucial for understanding how black holes form and grow. Gravitational waves have turned black holes from theoretical curiosities into real, measurable objects. We're finally uncovering their secrets. The universe's darkest monsters are now within our grasp. For millennia, we studied the universe with light. Gravitational waves give us a new sense, hearing the cosmos. Imagine living in a soundproof room, seeing but never hearing. Gravitational waves are our headphones. Now, we can detect events invisible to any telescope, like black hole mergers in total darkness. We can also combine gravitational waves and light, multi-messenger astronomy, for a complete view of cosmic events. This lets us measure the universe's expansion, probe neutron stars, and maybe even hear echoes from the Big Bang. Gravitational waves are a new tool for cosmology. opening up mysteries we never imagined. We've only just begun to listen, and already the universe is full of surprises. The symphony of the cosmos is playing and we finally have the instruments to hear it. Every detection is a new note in the universe's song. We're not just spectators, we're listeners. The universe is speaking and we're learning its language. The concert has only just begun, and the possibilities are endless. Gravitational waves haven't just confirmed theories, they've shattered them. In 2025, a signal called GW250114 revealed a black hole in the forbidden upper mass gap, about 85 times the Sun's mass. According to stellar models, such black holes shouldn't exist. Stars that massive should explode completely, leaving nothing behind. This discovery forced scientists to rethink how black holes form. Maybe it's a second-generation black hole born from earlier mergers, or maybe our models of stellar death are incomplete. One observation rewrote the rules and opened new mysteries. Science thrives on surprises like this. The universe is more creative than we imagined. Every new detection is a puzzle and an invitation to explore. Discoveries like GW250114 are more than anomalies. They're clues to the universe's history. By cataloging black hole mergers, we're piecing together the life cycles of stars and galaxies. Some black holes may be second or third generation, formed from earlier mergers in crowded star clusters, or perhaps our understanding of supernova physics needs revision. Each detection helps refine our models, revealing how the most massive stars live and die. We're becoming cosmic archaeologists, uncovering the universe's family tree. Patterns are emerging about mass, spin, and where these monsters live. We're rewriting the story of the cosmos, one gravitational wave at a time. From Einstein's prediction to LIGO's discovery, gravitational waves have transformed our connection to the cosmos. We've confirmed the foundations of physics and turned black holes into measurable realities. The field is young. New detectors and future missions like LISA will open even more of the universe's symphony. We might hear the echoes of the Big Bang or discover entirely new phenomena. Every detection is a chance to confirm, challenge, or rewrite what we know. We're explorers in a new sensory world, listening to the universe's vibrations. The concert of the cosmos is just beginning, and we have a front row seat.